and welcome to the third session of day 2 of this faculty development program on computational techniques in engineering. We are fortunate to have highly eminent resource person with us, Professor B.S. Pabla from NITTR Chandigarh. For this session, I will request my colleague, Dr. Arshad Hussain, to kindly take over and moderate this session. Dr. Arshad Hussain, please.
Thank you, Dr. Imran Shafiq. As Dr. Imran has already told you that we have all assembled here for the new presentation, a new lecture on engineering optimization, and the present we have Professor B.S. Pabla with us. I would like to present before you a brief introduction of Professor Pabla. So he is a very eminent person. Everybody in the field knows about him, but still he did his B.Sc engineering and M.Sc engineering from Punjab Engineering College, Chandigarh. Professor Pabla has done his Ph.D. from Punjab University, Chandigarh. He has worked as principal, Chandigarh College of Engineering and Technology, Chandigarh, from August 2007 to September 2010. He has worked as Dean in the Faculty of Engineering and Technology in Punjab University, Chandigarh. Presently, Professor Pabla is working as Dean Extension Services and Consultancy and Professor Mechanical Engineering Department at NITTR Chandigarh. He has also worked with DCM Engineering Products and Swaraj Mazda before joining NITTR Chandigarh. He has authored 3 books on CNC machines, which has been published by Wiley Limited, and he has numerous publications in journals of national and international repute. So I welcome you, sir, and would like to request you to please start your presentation on engineering optimization. Over to you, Professor P.S. Pabla, sir.
Thank you, Mazda. Thank you for a nice introduction. First of all, I would like to thank the coordinating team, principal, and management of Aligarh Muslim University Polytechnic for inviting me to be a part of this program, which is of highly relevant and very, very important for all of you, for all of us, in fact, as teachers, because we do talk about continuous learning, lifelong learning. We cannot, because it is so a dynamic process these days, technical education, that we cannot say that now I know things and I'll stop attending the classes. And in addition, it is mandatory as a part of the professional life also, because we need to attend some programs, but in spite of all the requirements, what I feel is that we should attend the programs seriously so that we have some takeaways from programs. The experts do their best. The coordinating team puts in a lot of effort in conducting these type of programs, and if the participants are not serious, I think it is a waste of effort, waste of time, waste of resources. It is our resources only, all of us are contributing to it. So I request you to please attend all the sessions seriously and sincerely. Another thing is that the coordinator session host may not allow you to talk in between. So I request you that you write your questions in the chat box. Make the session very interactive. I will see the chat box intermittently and try to answer your queries. So please do that, because otherwise the shortcomings of this type of program is that the speaker sometimes feels that he's talking to the walls of his room. There's nobody who is responding. Please do respond, ask questions to the extent possible. I don't know, I can't say that I know everything, but to the extent possible, I'll try to answer your queries. So I'll start with the presentation. Is it visible?
Yes, it is visible, sir.
Okay, thank you, thank you. Because somebody has to keep me telling because. Okay, Professor Afsar Hassan, I'll start now.
Yes, yes. Please go ahead, sir.
I have been asked to talk on engineering optimization, so I will take up the introductory part only. Now let's see what is optimization and what is engineering optimization. Optimization applied to engineering problems is when we try to solve the problems in engineering domain, then we call it as engineering optimization. It is not that optimization is used only in engineering. All other fields. In our homes, we do optimization. A dietitian does optimization. Economic professor in economics or a person economist, they do optimization. Medical people, they do optimization. Everybody does optimization, but we are talking about engineering optimization concerning our field. So we'll stick to engineering optimization or optimization in mechanical engineering. What is it actually? If you have to understand optimization, let us see. We have this is the simplest thing when if you want to explain optimization is the traveling salesman problem, which we study in mechanical engineering as a part of operation research. Let's say we have 4 stations, 1, 2, 3, 4, and we have a salesman. We have a person who has to visit all the 4 stations. There are distances which are known from one station to other stations, and there are costs involved. For example, if somebody wants to go from 1 to 2, it costs 10 units of money. But if somebody wants to go from 2 to 1, it costs only 5 units of money. So if given a chance, if I have to cover both the station 2 and 1, let's say we forget about 3 and 4, what I will do, I will first go to 2 and then go to 1. Because the cost involved in going from 2 to 1 is half of the cost which is involved in going from 1 to 2. Similarly, there is a condition that I have to cover all the stations, 1, 2, 3, 4. My requirement is that I want to, let's say, visit all these stations at minimum cost. The cost incurred should be minimum. Right? Then constraint that I should visit all the stations, 4 stations. Sometimes there can be additional requirement that I have to go to station number first. I cannot start from station 3, 4 or 2. So these are the limitations, these are the conditions placed on me. If I can find a route which can tell me, which can give me the minimum cost, that is the optimization, that is the optimum route, right? Now this is only 4 stations. I have just taken an illustration to start with, so that you are in line with, in tune with, in sync with me, what I want to talk today during these 2 hours. So this is what we call as optimization, but it is not end of it. It is not 4 nodes only, 4 stations only, 4 cities only. It is n number of cities, n number of stations. You see here I can do it manually. I can do permutation and combination that okay, I go to first, second, third, fourth, or I'll go to first, third, fourth, second, or I'll go to first, fourth, 3, 2. Whatever combinations are possible, I can manually calculate and I can find out what is the cost involved. But when the number of stations or the number of variables involved is more than, let's say, 5, 6 variables or 10 variables, it is very difficult to work manually, where we have to take help of the computer, where we write a program, which is a generic program, irrespective of the number of variables, it will give you a solution. So let's see. For example, we are, I presume that there are many of you are mechanical engineers. We do optimization of current parameters. Let's say we are machining on lathe. We have 3 cutting parameters. We have speed, feed, and depth of cut. And we want to, let's say, we want to maximize the tool life. So we write a equation where tool life is expressed in terms of V, D, and F, or cutting speed, feed, and depth of cut. If I can write a mathematical model, if I can do that, I can solve this problem. So optimization problem is essentially a mathematical modeling problem. We have to make a mathematical model to solve it. What is a mathematical model? Mathematical model is representing a physical phenomena in terms of mathematical terms, right? In terms of mathematics, we are trying to represent the physical phenomena. Now, simplest example is you have a line, let's say, so we write it y is equal to mx plus c. So y is equal to mx plus c is basically a mathematical model of line, which can represent any line. So example of optimization is optimization of cutting parameters for tool life. Another example can be optimization of cutting parameters for best or improving the surface finish. Optimization of cutting parameters for reducing the machining time or minimization of the machining time. Depends what I want. Optimization of the cutting parameters for minimum cost of the component, minimizing the cost of the machining operations. So that depends on me, what I want to do. I have given you 3-4 examples in optimization of cutting parameters itself, right? And that too on a lathe machine itself. But you can work on any machine. You can have the optimization problem on any machine. Another example, just see. Design of a steel structure for minimizing the weight without compromising on the strength. We want to design a cantilever. We want to design a simply supported beam. What should be the dimensions of the simply supported beam so that it will not fail at the same time? I want to let's reduce the weight. I want to reduce the weight. I want to reduce the cost. There is some message.
Sir, I think your slides are not changing. You are.
I am still on this first slide only.
Oh, okay, sorry, sir. Oh, please
I will
continue.
change. Okay. So we want to design a steel structure, because what I am talking is not written on the slide actually. I am just trying to take it literal. Then deciding product mix to maximize profit. Let's say somebody is making more than one products. What should be the product mix? How many products, how many items of a particular type one should make so that you can maximize the profit. Deciding on the layout of components on CPU for maximizing heat transfer. You see, now we are getting faster and faster computers. Earlier we used to have one fan in the CPU because there is a lot of heat generated inside the CPU. Now what is happening? They are starting putting 2 fans. That means there is a lot of heat generated inside the CPU. Now to take out that heat, what should be placement of the components in the CPU? In our example, let's say what should be placement of the machines in a machine shop so that my criteria is maximized or minimized. My traveling distances are minimized. My backtracking is minimized. That means backtracking means components coming from the further machines to the, let's say there are machines 1, 2, 3, 4 in the queue, in the line. So from 4 to 3, I want that there should be no component coming or minimum number of components coming. So how do I do this? I do maximization, I do line balancing, I do what type of jugglery I want to do, I do it, and basically it results into maximization or minimization. That means we may be trying to maximize something, we may be trying to maximize profit, we may be trying to minimize cost, we may be trying to maximize tool life, we may be trying to minimize surface roughness, whatever it should be, and that we have to decide. We as users, we as engineers, we as planners, we have to optimize what we want to do, whether we want to maximize something, whether we want to minimize something. So let's see the formal definitions. There are many formal definitions of this. Optimization, the act of obtaining the best results under given circumstances, very important. Two things are there. It is getting the best results. Now, getting the best results, everybody knows that we want to try to get the best results. But more important is under given circumstances. What are the circumstances under which you are operating? What are the resources you have? What are the environmental conditions? What is the financial position? I want to produce 1 lakh scooters in 1 month, but my financial resources do not allow this because I don't have money to procure the raw material for this. Right? Optimization can be defined as the process of finding the conditions that give the maximum or minimum of a function. Basically, we all have studied in mathematics maxima and minima, problems on maximization and minimization of a function. So optimization is based basically on maximum or minimum of a function we want to achieve. Optimization seeking methods are also known as mathematical programming techniques and are generally studied as a part of the operation research. We do that in mechanical engineering, we do study this. We do all this in operation research. We do it in mathematics also. So there are majority of the techniques, they are based on the mathematical programming or basically basic calculus, and there are other techniques which do not depend on this. Purpose of optimization is to achieve the best design relative to a set of prioritized criteria or constraints. I mean, we do have constraints. We do not have money. We do not have raw material. That is a constraint. Or there is a criteria. We want to reduce the cost of production. We want to increase the volume of production, quantity of production. We want to improve the quality, we want to improve the surface finish, whatever is important at that time. Maybe at some times we may be not be bothering about the surface finish, but we want more production. That means then the quantity produced becomes the criteria. But when at other components, maybe we are more concerned about the surface finish and we are not concerned about the quantity of the production. At the same time, there may be instances where you want both. You want best surface finish as well as the best quantity and maybe minimum cost also. So the purpose of optimization is to achieve the best design relative to a set of prioritized criteria or constraints. These include maximizing factors such as productivity, strength, reliability, longevity, efficiency, and utilization. Action of making best or most effective use of a situation of resource. When you have a constraint on resources, when you have sources which are costing you, which are adding to the cost of the component, we do talk about minimization of cost, maximization of productivity, improving of strength, reliability, efficiency, and utilization. I have already talked to you. We do make decisions or optimization techniques in day-to-day working also. We do. When I come to office from my home, I have a set route. Although I can have n number of routes, but I have a set route where I have studied actually that based on my past experience, what I have done is I have calculated or I have observed that if I go by route 1, I get minimum number of traffic lights. I have minimum traffic rush on that road. So I reach early. But when I have to go back at 5:30 or 6 o'clock, maybe that road is not suitable to me. So I optimize. Sometimes I say that this is a longer route, but it takes lesser time because there are no traffic lights, there are no vehicles or very little number of, lesser number of vehicles on the road. That means there I am ready to go by a longer vehicle, a longer road, because probably it is more convenient to me. And it may save me time. So we do have every day, in everyday life, in your kitchen, in your home, in your travel, you do make optimization decisions. In our engineering applications, we make decisions based on optimization in engineering design, manufacturing control and monitoring, inventory management, transportation, and whatnot. Everything, every day, in every instance, in every activity, we are trying to optimize it. Plant layout is another thing where if it is optimized, you keep saving throughout the life till you change the layout. Architecture people, they do optimize the buildings, they will do optimize the space. Nutrition. Nutrition is another area where you will find examples of optimization. How much of the particular type of component of, let's say, baby food should be mixed so that we get the required proteins and all, and at the same time, the cost should be low. In economics also, we do use, in fact, in every field, I said medical field, in economics, in agriculture, everywhere we use optimization. Now, there are basic terms in optimization. The first is either we minimize or we maximize, right? In fact, when you start studying optimization, you will find that minimization and maximization are almost similar things. If you multiply minimization by -1, it becomes maximization problem. That means a minimization problem can be converted into a maximization problem, and maximization problem can be converted into a minimization problem. What is the objective function? First thing to be defined in optimization is the objective function. An objective function expresses the main aim of the model, which is either to be minimized or maximized. So I said we want to maximize the tool life. So tool life in terms of, when we write tool life in terms of speed, feed, and depth of cut, then then becomes a objective function. When we write profit in terms of the profit made by each component, each product you make, and the number of products you are producing, then it becomes an objective function. So that means objective function is a mathematical equation. Either you minimize it or you maximize it. Cost you want to minimize and profit you want to maximize. So that depends on what you want. Design variable. A set of unknowns or variables which control the value of the objective function. Let's say I said we are working on a problem on cutting tool life. So what are the variables I said? It is V, D, and F. So V, D, and F are my design variable which I can change. And by changing these variables, the value of my tool life changes. So that means these are the variables which impact the value of the objective function. Constraints. These are the limitations on resources or design variables, what I said. These are the limitations. Limitation is, that means I want to increase the production of plastic chairs, but the quality of raw material, raw plastic, which I have, it is just sufficient for 300 chairs in a day. So that means that quality, this quantity of the plastic which is available as raw material to me, that becomes a constraint. So design variable is again a variable only. Design variable is a numerical input that is allowed to change during the design optimization. That means you can increment or decrement those values, and let's say coming back to our cutting tool life, Vt raised to power n or Vt raised to power n, P raised to power a, F raised to power b, and T raised to power c. That is my objective function, and the variables are V, F, and T. These are the design variables. No, but I cannot have infinite variation in depth of cut, in feed rate, and in speed, RPM. So that means they will have limits. They will have limits on that. So design vector, if you write all these variables, let's say we have V, F, and D variables, but I can write them as x1, x2, and x3, where x1 is V, x2 is F, and x3 is D. So if I can write them in the form of a vector, or I can write in the form of an array, that becomes a design vector that contains all the variables which we can change. So design vector is a set of design variables generally written in the form of a row matrix. That means instead of 5 variables, we will have a 1 into 5 element matrix. Design optimization is the process of defining the best design parameters that satisfy project requirements. So it may be design optimization, it may be machining optimization. It is a problem of optimization. You see, formulating the optimization problem is the very important part of optimization process. If you are not able to define the problem properly, if you are not able to make a mathematical model of the physical problem, you are not, in fact, you are bound to fail. You will not get the results what we want. So let's say somebody says it is a bad formulation. A chemical factory produces a chemical from two materials. There are two materials, X and Y, which are used for producing a chemical, whatever chemical, it may be a solution, it may be a product, right? X can be purchased for $5 per ton and Y can be purchased for $1 per ton. The manufacturer wants to determine the amount of each raw material required to reduce the cost per ton of product to a minimum. Formulate the problem as an optimization problem. It says it is a bad formula. It is a bad problem because there are many things missing actually in this. It is a very open statement. So it says minimize f of x and y. So what is that? It says it wants to reduce the cost per ton, isn't it? It wants to reduce the cost per ton. So the cost is function of what? Cost is, let's say you have x and y, 5 into x plus 1 into y. If you have 1 ton of x material and 1 ton of y material, that means you have $6 material. But let's say you want to put it in terms of variable. Let's say you have x quantity of first variable and y quantity of second variable, second material. Then what is the total cost? 5 into x plus 1 into y. That means I want to minimize this. Subject to what? Because it is basically two chemicals. The value of the quantity of the x and y cannot be less than 0. It has to be a non-negative quantity. This is called a subject to x is equal to or greater than 0, y is equal to greater than 0. This is called a non-negativity constraint. Right? So we want to minimize this. How do we minimize? There are probably many things missing. So it says minimum value will be if you have x is equal to 0 and y is equal to 0. They say you don't produce anything. The solution, what has to come? Because we have to minimize this. What is the minimum value of this? Is 0. Right? So that means this is a ill-defined problem. It is an ill-defined problem. It should give some more things. It should say that I have to produce minimum X, let's say 50 items, or I should have minimum this much quantity. There should be a limit on the X and Y, another limit. And then only you can define the problem. Otherwise, the problem is very simple. Is you don't produce anything and you will not consume anything. Given the perimeter of a rectangle must be at post 16 centimeter, dissect the rectangle with maximum area. Formulate this as an optimization problem. Let's see what it says. Let's say we have X and Y are the two sides of the rectangle. And what it says, the perimeter is 2x plus 2y. It should be equal to or less than 16 at the most we can. And x is equal to 0. Y, x cannot be negative and y cannot be negative. Those two sides cannot be negative. So this is another function which we can solve. This is not a okay. X and y it has come a non-linear problem because x is multiplied by y. We will come to it. What a non-linear problem is. So objective function is a single or multiple objective function. That means we can have a single objective function. We have some single objective that we want to reduce the cost, we want to minimize the cost. At the same time, I can have multiple objective functions, which says that I want to reduce the cost, at the same time, I want to increase the profit also, or I want to increase the volume of production also. That becomes a multiple objective function problem. And there are constraints. What are the constraints? There are equality constraints where you say, okay, axis lies between, let's say, 5 and 15, or you have equality sign. Inequality constraints is when you have less than equal to or more than equal to sign. Equality constraints means you say 2x plus 3y is equal to 5. That is the equality constraint. If you write 2x plus 3y is less than 5 or more than 5, that it becomes a inequality constraint. Then behavioral or functional constraint that limitations on the behavior and performance of the system, how the system behaves. At the same time, site constraints represent physical limitations on design variables such as availability, fabricability, and transportability. Very important criteria. You all know that we have all talked about that optimization is a iterative process. Iterative process means it goes on improving. Let's say we want to improve the profit. Profit comes 1 lakh. We will again iterate by changing the variables or coming to our tool life problem. It will calculate the tool life under given Ph.D. and it will note down. Then it will again do another iteration. Then it will compare the two values, previous iteration and current iteration, and it will give you which one is better. If it is improving, it will again increment some of the increment or decrement some of the variables and see the next value. So basically, it is the current value, then the neighboring value, and the difference between two. What I want to say here is that when we start iterative process, when will we stop? When will you stop? So there are different termination criteria. That means I can say that, okay, when 100 iterations are there, you stop, whatever is the value. Right? I can say that. Second is, I can say, okay, there is a current value, there is a new value coming. If the difference between them is very small, let's say you are trying to improve the profit. If the difference between current value and the new value is, let's say maybe less than 1,000 rupees, you say, okay, I am not bothered. I will stop it. I will not work on it more. And I will say, now this is my optimum. So, when to stop iteration, that is very important. So to stop this iteration, there are some different criteria. One is solution is sufficiently accurate. That means there is no change. What I wanted, that I should get 5 lakh as profit. Now if I am getting 4.9, 5.5, I will stop. Progress becomes too slow. The difference between the consecutive values is very small. It is, we call it terms of epsilon. Very small. Then we can say, okay, if the difference between the previous reading and the second reading and the current reading becomes very small, I can give a value. Let's say I say, okay, 0.001. Then the process should break. Maximum resources have been spent. There is a availability of resources is there, but now resources are not there. Maybe even one resource has gone. So there are two types of plastics. If one of them is gone, that means I should stop. Solution diverges. When I think the solution, when I am saying that the when I am saying that the process is I am improving, that when the solution is converging. Solution is converging. Converging means it is coming to a point. Okay. But if instead of converging, it is coming narrow, it started diverging, then we say that the solution has started diverging, so we will stop. We will stop. So the solution diverges or cycling recurs. Again and again we are getting the same values. Then also we have a termination criteria. That also is a termination criteria for us. You see, it is very important to first decide what is the termination criteria. I will say when there are 1 lakh iterations, stop it. Whatever value is there, I will accept it. When the difference between 2 consecutive values of objective function is, let's say, less than 1000, I will stop it. And I am talking about money part. If the surface finishes between the 2 consecutive runs or 3 consecutive runs is, the difference between them is, the values is very small, I stop it. Okay. So termination criteria is very important. There is another term. It's called local versus global minimum. You see, we are trying to have a value which given within the given range of variables. Let's say I say my depth of cut can vary from 0.1 to 5 millimeters. Now within that period, within that value of depth of cut and combination of feed and speed, I want that there should be no other point which should get a better surface finish in this range of turning speed. The value I get from my experimentation, from my optimization process, that should be minimum. Now within that range, there should be nothing which should be lesser than this. Or the cost should be minimum. There should be nothing which is lesser than that cost. But what happens? The process is basically, optimization is basically comparing the current value and the new value. You have a new value, then you have a neighboring value, next value, you calculate. So optimization is based on that. My termination criteria is based on that. But just see the figure. You have a figure which is plotted between -4 to 4x, and there are values of y which are varying from, well, let's say 400 to 0 to again 400. But if you are, let's say, somewhere here at +3, a minimum will come. And when the value of x changes 3 to plus, let's say 3 plus, it again started increasing. So at some time, the surface finish has come here as minimum. But when you change the value, when you increment the x value, this goes and start increasing. So you get a false impression that we have reached a minimum value of cost or minimum value of surface finish. But if you see on the graph, this is not the minimum value. This is not the minimum value. Where is the minimum value? Minimum value is this. Although if I have to operate between 2 and 4, this is the minimum value. But when I am operating from between -4 and 4, this is the minimum value. So this value, which has come at around 3 or 3.5, 3.7, whatever it is, this is called a local minima or local maxima. Similar, I can get a maximum value also. But when I come here, now there is no value in this on this graph which is lesser than this value, right? Whereas when I was here, there was a value lesser than this here. So this is my global minima in the given range of variables. X is varying from -4 to 4. Maybe if I go to, let's say, -8 or +10, I will get another global minima. You see, when I have come at this point between 2 and 4 at, let's say, 3.5, it gives a false impression that I have reached a minimum value, whereas it is not minimum. It is local minimum. So when you are held up in this, you have to try very hard to get out of this trap, and so that you can explore further values. Otherwise, depending upon the termination criteria, the optimization process will break here. Mathematical models say it has found a new value. But to be very clear that we have operated between -4 to 4, we need to keep the program running. So it is a difficult thing how to find out whether we want to continue or we want to terminate the process. Okay, let us see, some chat is there. Yes, it is given. Professor, this is global minima is in the given range. Now it is the minimum value. There is no other value which will be less than this value between the -4 and 4. Whereas if I take this 3.5, 3.7 value, and I am talking about -4 to 4, I have this as minimum value, but there is another value which is lesser than this. So if there is another value which is lesser than this value, it is not a global minima, it is a local minima. Similarly, I can have a maximum here, but I have global maximum is here. There is no other point where my function is more than this value. So basically, in simple terms, what we say is that there is no other value which is lesser than this. But if I, let's say, expand my range, okay, let's say I say, okay, I don't want to work between -4 and 4. I want to work between 0 and 4. Or 0 and 6, 5. So then this becomes my global minima, local as well as global. If I want to say that I want to work between -4 and 0, this is my local as well. This is my global minima. Maybe you can get another minima here, near 0. So this is what when we say that it is local minima or global minima. So I hope this is clear. Let's say we say find X or minimize. It is between find X is a, what is X? ऊपर वाला जो X है, that is a design vector. It is combination of, it is a, basically there are n values, x1, x2, xn. Like in my two life equation, we had 3 values, B, F, and D. Here there are n values. This is the design vector, right? Now fx, which minimizes fx. You see, this is an incomplete definition. Minimizes fx, I should write when fx is equal to, I should write in the term of a form of a mathematical function that fx is equal to x1 raised to power n, x2 raised to power n plus 1, something like that. Or x3 plus 4x2, something like that. Okay, plus n and xn. So I need to find the values of x1, x2, and xn up till xn which will give the minimum value of fx, where fx is the function of x1, x2 till xn. Subject to the constraint. What are the constraints? That gj, that means g constraints for j is equal to 1 to m is equal to or less than 0. That means gj, that constraint, this will not be g, this will be some value, this will be some equation, let's say, or it will be, let's say, x1 is less than 0. So these are gj x is equal to less than 0. These are called inequality constraints. And there is a sign of inequality in it. Lj x is equal to 0. That means x1 plus x2 plus x3 or 5x4, that is equal to 0. That means there is a relation between x1, x2, x3, x4. This is called an equality constraint. Then again it says x1 to xn is equal to or greater than 0. That means when I said gj, I can say x is less than 5. No, x is not less than 0. It can be between 0 and 5. But at the same time, it says x1 to xn are more than or equal to 0. This is called a non-negativity constraint, that x1 and to xn, all these variables, they cannot be negative. Either they can be, at the most, they can be 0 or they have to be more than 0. So here, if you see, the top x is called the design vector, fx is the objective function, gj are the inequality constraints, and lj are the equality constraints. We will understand it more in the coming slides. Now let's say how are the optimization classified. Because there are many methods, where there are many approaches to optimization. We can say constrained and unconstrained optimization problems. Constrained optimization problems are subject to one or more constraints. Unconstrained optimization problem, there are no constraints. These are open. But we will normally have constrained optimization problem. In mechanical engineering, we will have, let's say, constraint on resources, constraint on outcomes. Let's say we want surface finish less than or equal to something. RPM should vary between 20 to 2000. Feed rate should vary between these two values. So we will have, depending on whether we have constraints defined or not, we can call it as a constrained or unconstrained optimization problem. These are classical methods, right? Under those only, under those constraints. Anyway, we will have more classification. This slide, this incomplete slide. Linear programming. What is linear programming? When we call the linear, when all the objective function, that means objective function is a mathematical equation, and all the constraints are linear functions of design variables. When it is linear, when we say that in our terms, when we talk, we say the power of any variable in the objective function or in the constraint is 1. Right? It can be a constant, but power cannot be more than, it cannot be x square, x cube, something like that. It is only x, x1, x2, x3. It can be 5x2, 10x2, 20x2, 100x2, something like that. But neither in the objective function nor in the constraints, there is a power raised to power, any variable raised to power more than 1. Even if you write x into y, x1, x2, that also becomes raised to power 2. Right? That also becomes it doesn't remain a linear optimization problem. Non-linear programming is when any of the functions, either in the objective function or in the constraints, is a non-linear. Even when you have x1 into x2 or x2 into xn, that becomes a non-linear problem. Geometric programming. When the objective function are object basically and constraints are expressed as basically polynomials, actually polynomials. And we have a quadratic program. We know that it is a non-linear programming problem with a quadratic objective function and linear constraints. Quadratic function, we know what is that. That is raised to power 2 only. Then we have integer value problems and real value problem. What is the integer value problem? Integer value problem is where the variables cannot take discrete values. Continuous values. Let's say variable can be 10, but it cannot be 10.1. It cannot be 9.2. It cannot be 4.5. It can be 4, 5. So it can have only integer values, right? This type of problem. Let's say if you want to say how many machines you want to employ, I cannot say I will employ 1.2 machines, or how much manpower I want to have. I will not say that I will have 1.2 persons. I will have either 1 person or 2 person. 1 person probably will not suffice. I will have 2 person only. So where the variables are restricted to take only discrete values or integer values, then we call it as an integer programming problem. Integer programming problem is basically extended form of linear programming only, where we restrict the values to linears. That means this is more than linear programming. Then real value programming problems. Maximum or maximize or minimize or maximize a real function by systematically choosing the values of real variables from within an allowed set. You see, range is there, but I can have 5.1, I can have 5.2, I can have 6.8. When the allowed set contains only real values, it is called a real value program. But it can have a continuous value of the variables. It is not restricted to integer values or discrete values. It is like our voltmeter, either it is analogous or it is digital. So when you have digital values 1, 2, 3, 4, not decimal. I cannot have 1.4, 1.3, no. 1.3, I can have 1, 2, 3, 4. Then it is an integer programming problem. When you have a real values, decimal values, then you have a real value programming problem. Deterministic or stochastic problems. Deterministic means you have a control. You know the values of the variables. They cannot change. They will follow a pattern. So in deterministic system, for the same input, the system will produce the same output always. In this type of problem, all the design variables are deterministic. You know it. There is no fuzziness. There is no variation. You know that it can be 0.1, 0.2, 0.3, or the feed rate can be between, let's say, 0.1 to 0.75. That is all. But in stochastic programming problems, some or all of the design variables have probability of having some value. That means there is a probability. It may rain, it may not rain. So stochastic programming is a framework for modeling optimization problems that involve uncertainty. That means the values are not clear, values not fixed, that it's not clear that we will have these values of the variables. Then these you see, we may not be appreciating this, but these are the real things, especially where human behavior is involved. Separable and non-separable problem. Separable problem, this type of problem, the objective function and the constraints are separable. The function is said to be separable if it can be expressed as sum of the n single variable problems. what is this? That means, let's say you have a function fx is equal to x square. Can I replace this x square by, let's say, x1 plus x2 plus x3, or x1 plus 2x1 x2 plus 3x3 plus 4x4 or 10x5? If I can approximate that function, then maybe with some little error, then this is a separable program programming problem. Where is a non-separable program problem is not objective function is not separable. That means you have to work it as a square only. X square, if it is x square, then you have to have it x square only. You cannot put it into in single variable functions. Single objective program, there is only a single objective function. That means I want to reduce the cost, that is the aim. I want to increase the production, that is the aim. I want to reduce the rejection, that is the aim. I want to improve the surface finish, that is the aim. But there are conflicting situations where I want to decrease the cost of production, at the same time I want to increase profit, or I want to improve the surface finish, at the same time I want to increase my profit. So that maybe when you want to improve the surface finish, you need better machines, which will add to the cost of manufacturing. That means there are conflicting things. I want to improve the, I want to get better surface finish, but I want to reduce the cost also. So these are conflicting things. So when we have more than one objective function, we write it as a multiple objective programming. Multiple objective functions you have, and you convert it into a single function by giving weightage. That means if there is a weightage is 1, I will say, okay, I give 0.8%, 0.8 weightage to my surface finish and 0.2 my cost. Or I give more weightage to the cost and less weightage to the surface finish. That depends what I want. So I can have a single program multi-objective function, which is basically weighted average, weighted values of different objective functions. Then we call it as classical methods and new methods. The classical optimal techniques are useful in finding the optimal solution or unconstrained maximum or minimum of continuous and differentiable functions. You see, classical methods are basically, they are based on calculus, differentiation. And they want that if you want to have a minimum or maximum of a function, it should be continuously differentiable. Whereas in practical problems, the function may not be continuously differentiable. So then these classical classical optimization techniques, they fail. Okay, it is written. These are analytical methods and make use of differential calculus in locating the optimum solution. The classical methods have limited scope in practical applications, and some of them involve objective functions which are not continuous and or differentiable. Yet we need to the study of these classical techniques of optimization forms the basis for developing most of the numerical techniques that have evolved into advanced techniques more suitable to today's practical problems. We don't use this differentiation and all. We are talking about now these many people you will find that they are talking about genetic algorithms. They are talking about ant colony optimization. They are talking about bacterial foraging optimization. They are basically getting inspiration from natural phenomena. We'll come to it that let's say GA, genetic algorithm, that is basically based on the concept that fittest will survive. We'll come to it. These methods assume that the function is differentiable twice with respect to the design variable and the derivatives are continuous. There are three main types of problems can be handled by classical optimization techniques: single variable functions, multivariable function with no constraints, multivariable function with both equality and inequality constraints. And problem with equality constraint, the Lagrangian multiplier method can be used. If the problem has inequality constraint, the Dekker conditions can be used to identify the optimum solution. That means Lagrangian multiplier is one method. Dekker conditions are basically the necessary and sufficient conditions if the problem has to have a solution in optimization, not minimum or maximum. These methods lead to set of nonlinear simultaneous equations that may be difficult to solve. No question in the chat, so I'll continue. Now let's see a problem, small problem. This is a linear programming problem. It says one of the industries, the total production should not exceed 700,000. It is producing two items, product A and product B, in dozens. Now we are talking about in dozens only. It says the total production, because there is no demand more than 700,000, so why should we produce more than 700,000? So that is, there is a limit on the total production. That means if you are producing X of component A and Y of component B, then X plus Y should be equal to or less than 700. And the number of dozens of product A cannot exceed the number of dozens of product B by more than 350. If X is the number of dozens of A and Y is the number of dozens of B, then X minus Y should be equal to or less than 350. You see, why should we put it? Let's say, okay, let's say the product A gives me 5 rupees profit per dozen. Product B gives me 2 rupees per dozen. So, if I want to think as a layman, I will say I will produce only what gives me 5 rupees a dozen, because that profit is more per dozen. So I will produce only item A. But there are constraints actually. It is not that simple. Their companies want to remain in market, so they want to be out of market for product B. So they say no, minimum we will produce this. The maximum difference between X and Y should not be more than 350. So they have put a constraint on this. Otherwise, if it is free, unconstrained, I will produce only A item, product A, and if there is some material left, then I will produce product B. So that means this constraint is that X minus Y should be less than or equal to 350, and X plus Y should be equal to or less than 700. Then there are technological inputs. Product A requires 2 kg of plastic. This is the requirement. And 3 minutes of labor. That means there are 2 things on a machine. It will take one dozen of product A will take 2 kg of plastic material and 3 minutes of labor or machine, whatever. And product B requires 1 kg of plastic and 4 minutes of labor per dozen. Right? So just keep in mind what I have taught. Now, what the current production plan says? He says the product producing as much as possible of the more profitable product A, because it gives 8 rupees profit per dozen. That is what I said. I would like to produce more of A. But there is a constraint that X, the product A minus 20 of product A minus 20 of product B should be equal to less than 350. Use resources left over to produce product B, which gives 5 rupees profit per dozen. That is my thinking, that is your thinking also, but if there are no constraints. Now the current production plan consists of product A, they say they make 450 dozen, and product B makes 100 dozen. So if you want to calculate the profit, it will be 450 into 8 plus 100 into 5. So it will be 450 into 8 is 36 plus 5, 41 rupees, 100 rupees per week. This is the current profit. Now let's see how linear programming solve this problem. Can we improve this profit? The management is seeking a production schedule that will increase the profit. So let us see what a linear programming model can provide us an insight and an intelligent solution to this problem without violating the constraints. There are two design variables now, X1. X1 is the weekly production of product A and X2 is the weekly production level of product B. Then we have decided that we will produce X1, X2, X1, X2 becomes the variables which can change during the optimization process. Then what is the objective function? Weekly profit to be maximized. That means X1 into 8 plus X2 into 5, that is to be maximized if I want to write it in mathematical form. So just see, maximize 8x1 plus 5x2. That is the objective function, that is fx. Fx is equal to 8x1 plus 5x2. And what is the design vector? Design vector is x1, x2. What is the source requirement? Let's say it says 2 kg of plastic, 2 into x1 or 2 kg of plastic in per unit of x1 or per dozen of x1 and 1 kg of plastic in per dozen of x2. So that means 2 into x1 plus 1 into x2. The total plastic available is 1000 kg. That means it should be, I do not have more than 1000 kg. So I cannot consume more than 1000 kg of plastic. Similarly, production time. 1 dozen of A item takes 3 minutes. So 3 into x1 plus 1 dozen of x2 takes 4 minutes on the machine or the labor. That means 3x1 plus 4x2 is equal to less than 24. That is why the limit on my production time. That means I do not have more than 2400 minutes available. Now let's see what are the marketing constraints. It says x1 plus x2 should be equal to less than 700. The total production number of units should be equal to or less than 700. And the difference between the number of dozens of product A and product B should be equal to less than 350. And xj, that means x1 and x2 cannot be less than 0. They have to be either 0 or more than 0. Positivity constraint or non-negativity constraint. If you have understood this, I think you can make a linear programming problem. You can define the problem. This is how you define the problem. Now, how do you solve this? You can solve it graphically, right? So what we have done is we have plotted the constraints on this. So what is the feasible area? Feasible area is basically where none of the constraint is bypassed. All the constraints are satisfied. So what has been done? This plastic constraint is this, total production constraint is this, production time constraint is this. So I cannot have a quantity which is here. I cannot have quantity which is there. Because if I go to, let's say, this point, this plastic constraint is satisfied, but not the other two. If I go to this point, the plastic, this total production time and production time is total production constraint and production time constraint is satisfied, but not the plastic constraint. Right here, this constraint is almost redundant because it is taken over by it is covered by overshadowed by the other constraints. Now this green area is your feasible area, and this pink area This is infeasible area. Whatever you want to produce, right? This is x1 and this is x2. Y-axis is x2 and x-axis is x1. So whatever you want to produce, that should lie in this green area. That is the only feasible region. If you produce something here in the pink area, that you are going to violate the constraints. So you will not have the resources for that. So the feasible area is green area, and the value can be at the corners, at this corner, at this corner, or this corner, right? Just see, this is same. The only thing is it has marked something like that. So what we have is we will have a value either on these lines also, and most probably on the corner points. So I can calculate it, you can calculate it also, I can do it mathematically also, I can do it graphically also. Because since there are only two variables, I can do it mathematically, manually also. But if the number of variables increases, it is very difficult to solve the problems manually. Another method is constrained and unconstrained, I said. Static optimization problem and dynamic optimization problem. Static is that means you solve the problem and keep using those variables, values, like we had this in Rama industry problem. Once you decide what is the value of x1 and what is the value of x2, you keep using that. That is a static optimization problem. But dynamic optimization problem is there are dynamic, let's say, process control. Let's say the RPM of the motor has to be controlled based on the temperature. So you sense the temperature, give it under in the optimization problem, and dynamically you control the system. Nonlinear programming problem, I said, I have told everything about this. This also we discussed, this is actually repetition of this. Now, what are the challenges and issues in this? Why are we failing in optimization of this optimization problems? Because there are two partners in optimization problem. Unless you are very efficient programmer and you understand optimization, most of the time you will feel that we as engineers, we are users of optimization techniques. We don't develop it. So what happens? There's a domain expert. Domain experts, we know what we are doing, but there is an expert who is a solution provider. Solution provider is, let's say, a computer people. When we talk to these computer flippers or solution provider or the customer talks to me as a solution provider, I don't understand the problem completely, or I don't take the data completely, because the normal consumer will not know what is the mathematical model. If I have not taken all the requirements from the customer and I have not converted into a mathematical model, I'm likely to fail in optimization issues. So the understanding of the optimization and the expectation from it by the solution provider and the customer are often substantially different. If the customer wants something he is not able to explain, or the solution provider is not understanding it, probably you will find that you are not able to give the correct solution, because we are not able to been able to mathematically model the process correctly. We have probably forgotten something, we have left some. As I said, solution provider may suffer from insufficient problem domain knowledge, while the customer from not being familiar with the basic concept of optimization. As I said, the customer will not know what you want. He only can give his requirements. Then you have to extract information from him as a solution provider. If you do not understand it, probably you have to devote some time in understanding the problem. what is the process, what is the domain actually. Then only you can give a proper solution. Typical values of objectives are typically, optimal values of the objectives are typically unknown. They do not have idea what should be the typical value. Then you do not know where to stop. Anyway, these are some of the applications. Dealing with an industrial optimization problem rarely starts with a given problem formulation. In contrast, formulating the problem in most cases represents a significant part of optimization problem. That means project is their optimization. Ideally, what should happen? The problem should be formulated first, then start optimization. But what people do is the formulation of the problem itself is taken as a part of the optimization project. Not many real world problems match those from the textbooks. Textbook is very simple because what we know we write. But in real life, they involve peculiar in the form of specific constraints, objectives, or additional requirements for result assessment. That means it is not a simple problem. It is a complex problem. Actually, you need those who have seen the NBA process. They say when my student pass out of my program, they will be able to give solution to complex engineering problems in mechanical engineering. So we are talking about complex problems. We should be able to map. We should be able to model the physical phenomena, complex engineering problem into mathematical models. If you are not able to capture the total information, then we are likely to fail. So it is the same thing actually. Now these are the simple problems. There are, because the time is also running. So there are optimization, advanced optimization techniques. These are, there are many, right? These are based on natural phenomena. Let's say I'll come to genetic algorithm. Genetic algorithm is basically survival of fittest. That means whatever is fit, that we will go along that. Whatever is not giving the desired results, we will leave it at that place. Right? People say that lioness, when it gives birth to many cubs, those who cannot walk or who have some problem, the lioness kills them at that stage of. Only the healthy ones he will carry. Similarly, simulated annealing. Simulated annealing has come from mechanical engineering. We have annealing process. What we do is we take it to a very high temperature, then slowly we cool down. But here it is again going to the top at a very fast rate, and then in between also you can find out which is the best way to go. And colony optimization, this is very important. If you see the bees, honey bees, when they go out from there, you see that web is there, where the honey is there. When they go out from the web, they go out in this different direction. But when they come back in a single queue. That means all of them take a single path. That is basically optimized path. They optimize the path and they follow that. Similarly, you must have seen the birds flying in the sky. When there is a group of birds flying in the sky, they will form a particular shape, which gives the minimum distance. Aeroplane is designed on the same shape. So we are trying to copy. What is the shape of the fish? So that we can copy the path of minimum distance. There is a technique called hill climbing. Is a graph search algorithm. These are basically search algorithms, search techniques. How to go to a optimal solution. Simulated annealing. Let's see what is genetic algorithm. Genetic algorithm is a local search technique used to find approximate solution to optimization and search problems. GAs, genetic algorithms, are a particular class of evolutionary algorithms. These are called evolutionary algorithms because they are evolving. That use techniques inspired by evolutionary biology such as inheritance, mutation, selection, and crossover. Right? That means you have two solutions, good solution, half of it or 80% of one solution you take, 20% of another solution to take. You make a good what is it? You make a better child solution from the parents. GAs are typically implemented as a computer simulation in which a population of abstract representations called chromosomes of candidate solutions called individuals who an optimization proven evolves toward better solution. That means you keep on trying combinations. There are, you see, they write it as an array, or they write it in a binary form 0101, right? Then half of it you take, half of the first individual, half of it of the second individual. Just see what results it takes. If it gives you better results from the previous results, take it, go ahead. If it doesn't give, leave it there. Try some other combination. This is what I said there. On finding food returned to them only while laying on pheromone. That means they leave small drops of liquid, which the other bees coming after the particular bee, they can smell it and they travel by the same path. Okay, this is the traveling salesman problem. I can do it manually here because what I have done is I have calculated the cost of traveling from 1, 2, 3. I have made all the permutation combination. I can go by 1, 2, 3, 4, 1. I can go by 1, 2, 4, 3, 1. I can go by 1, 3, 4, 2, 1. I can go by 1, 3, 2, 4, 1. I can go by 1, 4, 2, 3, 1. I can go by 1, 4, 3, 2, 1. Right? So I have added the cost of the path. I have made a matrix. It is from 2, that is from 1 to 1, 0, from 1 to 2, 10, but from 2 to 1 is 5. So if I have calculated the total cost, I have made the minimum cost of the minimum cost path is 35. That means this one is the minimum cost. But there I have only 4 cities to visit. If there are 20 cities to visit, probably I will not be able to do it because the number of alternatives will be very high. Anyway, so this is what I wanted to say. If you have any questions, please do let me know because optimization in itself is a big subject. It cannot be. I have just tried to introduce you to optimization. I probably could not have covered more in this small 1.5 hours. I am told that I have to give some time for the questions also.
Okay. We are very much thankful to you, Professor B.S. Pabla Saab, for such a nice presentation on optimization techniques. So we are thankful for your wonderful insight into the topic, and I hope the participants would have found it very engrossing as well as interesting for the knowledge sake. Anyone of the participants want to ask any question? You can. Nobody has written any question in the chat box till now. So you are welcome to ask questions. You can unmute yourself and ask a question if you want. Anyone? So if the participants are not asking questions, sir, I would like to request you one question I want to ask.
Yeah, please, welcome.
With your permission, please, sir. Which optimization problems are bound to produce better results, which have constrained or unconstrained problems?
Person, it is not a question of constrained or unconstrained. What type of situation you are in, right?
Okay.
Normally, in engineering, we will have a constrained problem only. We will have a constraint on resources. We have a constraint on machine time. We have a constraint on space. So we normally will be working in constraint optimization techniques only as mechanical engineers. For mathematics, they can have that maximize x square plus 3x plus 5, which probably I don't have any meaning to attach to it as a user, as a mechanical engineer. So I understand better the constraint problem, because unless there is a constraint, there is no use of optimizing also.
Yes, sir. So one more question, sir. What is the difference between implicit decision variable and an explicit decision variable?
Not much difference. Implicit is basically what I feel is clearly defined. Explicit may not be defined, but I am not very clear about this. Okay.
Okay.
Yeah.
Okay. Okay. Thank you.
Thank you. Thank you.
So if the participants are interested, they can ask the question, or we should end the session now. Okay, sir. So nobody is wants to ask a question. So I would like to thank you once again for sparing your valuable time to be with us and give such an extensive and interesting lecture on this topic of optimization techniques. We would like to have sometime soon another. We would like to join you soon, and I would like to thank you so very much.
Thank you, Professor. Thank you, Professor. Thanks a lot for inviting me for this.
Thanks.
Thank you.
Thanks.